Good morning. I'm now going to do the very last section of the book, chapter 30. And it's really words only 36 to 40, but I gave you a little blurb there because I wanted to prove to you, and this is all true. So please read the blurb. The blurb says, this priest, Lemaitre, okay, blah, blah, blah. He was the first person to propose a theory of the expansion of the universe widely misattributed to Edwin Hubble. He did this, of course, before they had any evidence. He was also the first to derive what is now known as Hubble's law and made the first estimation of what is now called the Hubble constant, published in 1927, 2 years before Hubble's article. Lemaitre also proposed what became known as the Big Bang theory. Now, what happened? At this time, Einstein, while not taking exception to the mathematics of Lemaitre's theory, and this is what he said, I can't read the French, but this is what he said, your calculations are correct, but your physics is atrocious. So Einstein did not want to accept the expanding physics theory. But then Hubble came along, and then that same year, Lemaitre returned to the MIT to present his doctoral thesis on the gravitational field of the fluid sphere of the universe and so forth. And he was there with Hubble and Einstein when Einstein had to say it was the worst mistake in his career not accepting that. But did he give credit back to our little friend? No. Lemaitre actually, he had a position of the astronomer in the Vatican, okay? And of course, their observatory and so forth in a crowded city and so forth with lights was unable to see the expanding universe in that small instrument. Now, you've had word 36 before. Big Bang Theory, Middle English, Big Bang, Bang, Bing, Bang, Bang, Old English, okay, Bonga, 2 pounds, whammo. The theory that all matter and energy in the universe was compressed into an extremely small volume that 13 to 15 billion years ago exploded and been expanding in all directions. Oof. Wow. Okay, now, how do you prove this, or how do you get something? What's the opposite of that? The steady state theory. This is what I think Einstein really wanted. New matter is constantly being created everywhere in the universe. Galaxies continually move out and are lost in endless space, and new ones occur or are created. Or the pulsating theory. We might be going out, expanding, 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 then you slow down, then you begin to contract, 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 contract again. And that is a pulsating theory, from pulso, pulsare, pulsare, pulsatum, to beat. The universe expands after the Big Bang, then it contracts in upon itself, explodes again to expand once more. So of those 3 theories, most astronomers like number 36, the Big Bang theory. Why? Because we have these things. You have cosmic background radiation. Radio, radiare, radiavi, radiatum to shine. The radiation uniformly detected from every direction in space, considered the remnant of the Big Bang. Well, if that's there, where did it come from? And most astronomers think from the single Big Bang. That's another way of getting some evidence. Not only do we see everything expanding. Now, I gave you that wonderful example. Think of a balloon. A round balloon. I want you to put black dots on it. Okay? Now, I don't want you to think the black dots are getting bigger, but they will in this model. Blow the balloon up, and the black dots are moving away from the expanding universe. And each one of you, say you had 14 dots on there, no matter what dot you were on, it looks like when you're the universe expanding, it looks like you're the center and everything is expanding away from you. And yet, if you're on any other dot, it looks like you were the center of the universe. That's why I said in chapter 1 or chapter 2, the center of the universe is everywhere and nowhere at the same time, and you all thought I was crazy. But that's the Big Bang Theory. The Big Bang Theory. All right, cosmic radiation sort of supports that. Dark matter, the last word, Middle English, dark and massa, masse, feminine, mass. The 23% of the universe that does not give off light but has gravity that can be detected. The kind of matter that humans, the planets, the stars, and the matter between the stars make up 4% of the unknown universe. Now, the newest textbooks think the dark matter is even greater than 23%, but your book has it. I said this book is very good, even as an old publication. I think it's about 10 years old, I think. The only chapter that's sort of out of date is this chapter, because they found all kinds of planets, all kinds of other moons, all kinds of things, and these theories are changing what is black matter, what is dark matter, and what is this cosmic radiation and so forth. But the rest of this is all very up to date. So please read pages 793, I can't read my numbers, and I love the picture on page 794. And that is following the Big Bang, matter and energy began to take shape. But the universe as we know it did not begin forming until the temperature cooled by billions of degrees. So if you look at that diagram, again, it's just a model, a man-made representation of what we think the Big Bang was. So look at that diagram, please. All right. Then go to the page, on page 796. You want to answer those questions. Look at the diagram up there on the top of the page. Dark energy, 73%. Dark matter, 23%. So it's how do you get all this energy? Don't forget then, on your own, to do the review questions in 798 and 799, and the review questions on 800 and 801. I'll have Miss Kelly put all of these onto the, what do you call it?
Google.
On Google, so you can study ahead, and I hope you do very well, and I hope I can see you on the final, and it's very exciting. Remember, this last chapter is very important, and you'll have fun on the last chapter. Remember, it's 26, 27, 28, 29, 30, one of the last 5 chapters, and I know you'll do very well because you're all brighter than me. Goodbye.